All right. So now we'll talk about kernel debugging. Kernel is the heart of the operating system that must be in memory all the time it's running. And if you have a bug and a crash in a user land code, the code you launch from the command prompt or the start or the desktop, then it doesn't crash the machine. It just pops up a box saying your app has crashed. Would you like to restart it or something? But if you have an error in the kernel, your machine dies with the blue screen of death, which is why Microsoft has learned to try to keep everybody else's code out of the kernel. They would really like the kernel to include only Microsoft written code, but unfortunately, it includes device drivers from hardware manufacturers who are often sloppy and imperfect about it, and Microsoft is always trying to make it better. So here's how it works. You have user applications. Remember the general rule, everything in Microsoft is named the opposite of what it is. So kernel 32 is not the kernel. It is the userland library to access the kernel. It then calls ntdil, which is the native API. Now, the way you're supposed to write Microsoft software, if you are a non-Microsoft developer, is by using kernel 32. And the programs we've looked at so far, we're using kernel 32. This is called the native API. The functions provided here are more powerful, but largely undocumented, and they're often used by malware authors for that reason. So that you can bypass kernel 32 and call ntdil directly. It's just more difficult to write your code, and it tends to bypass some security tools too. But anyway, this is all userland. Then it goes to the kernel. This is the actual kernel, ntoskernel.exe. That's what loads into RAM when you boot up the machine before you log in. And that then communicates with kernel data structures like device drivers to control the hardware. So you can examine NTOS kernel with CFF Explorer, and you'll see that it just has an awful lot of functions, starting with ALPS, create security content. It has hundreds and hundreds of kernel functions, which are the low-level API that controls everything Windows does. Everything Windows does just calls these routines. You don't have the authority as a userland program to touch the hardware at all. You have to ask Windows to please touch the hardware for you. Open a window, read the keyboard, and all that jazz. And all Windows software is doing is making calls that ultimately call these kernel functions over and over to do everything. So I've already enabled local debugging on this machine. It is an adjustment in the boot menu you have to make, BCD edit, and then you have to restart your machine to enable you to debug the kernel on your local machine. Now, until recently, it took two machines connected by a serial table to debug the kernel, because if you put a breakpoint in the kernel, and it stops, that machine is frozen. So the way you did it was you remote controlled it with another Windows machine with a serial cable. But those are 25-pin serial cables, and those are kind of out of date beyond belief. So Microsoft added more and more features to it. And when Mark Russinovich came in with Microsoft's acquisition of sysinternals, he added the feature to debug the kernel on your existing machine. Now, you cannot put a breakpoint in the kernel or your machine would freeze, but you can inspect the kernel. And the way it does that is it makes a crash dump of kernel memory and then lets you look at the crash dump. It does that for you. At least that's the way his earlier tool did, and I'm pretty sure that's how this tool still works. So we launch WinDebug as administrator, because you do have to have administrator rights to debug the kernel. All right. And now you can just connect to the local kernel. Before we used file launch executable, but now we're going to do file attached to kernel. And it has the option of connecting to another machine through various kinds of cables, but we're going to debug the local kernel, which is just going to look at the kernel on the existing machine. And so now I'm connected. And all right, now I can see the loaded modules in the kernel with LM. And here they are. When NT is NTOS kernel, it's the only module with a shortcut. And here's some more things that are loaded. And so if you click the NT, it will show you details about that. This is the sense in which it is a GUI. And now you can click functions, and you will see how useless this attempt to make this into a graphical utility is. What that did is it listed all the kernel functions that start with the letter A in alphabetical order, and there are hundreds of them. So putting them in a long list in this window is kind of useless and pointless. And if you go back to here, you'll see it offers you other letters to click, each of which will make a huge list too big to fit in the window. And it shows you what it actually did was just type in this command for you. So all the pros ignore this GUI nonsense and they just learn the command line commands to control WinDbg. It's extremely powerful, but you have to learn the command line commands. And the best way to learn them is the local help. This is a Windows 3.1 chum file, which teaches you this. So here I'm going to use the X command, X/D. So you put in X and go to examine. And this will teach you how to use the commands. And often they are very confusing. The syntax is strange, and you have to carefully read this to figure out how to use the commands. This is how you learn how to use WinDbg. And with WinDbg, you can totally examine the Windows kernel and figure out all their secrets. So there really are no undocumented functions. It is not very difficult to look directly in the kernel and figure out what the functions do. There are ones where Microsoft hasn't published documentation, but it's not at all out of reach to just use WinDbg to figure out how it works. So anyway, all right, we've been there. So now that's help. Okay. And so now there's a flag you can find by just looking for a word you'll see in there. And then let's disassemble a function. So I can unassemble function with UF, and I'm going to do one of the kernel functions. So it's ntbang, and I'm going to do ntCreateFile, a function used by Notepad and many other programs that create a file. So now I've disassembled the function, and this is it. It's not very big at all. Looks like about 20 lines of ARM assembly code because it's just going to call another thing, IOP create file. A lot of the functions are just shells that rearrange the variables and then call an older, simpler function. All right. Anyway, and so you have addresses. That's what this is. This is a 64-bit address with an apostrophe put in the middle to break it into two 32-bit chunks to make it easier to read. This is the 32 bits of data, which compose an ARM assembly language command, and this is the ARM assembly language command that moves things in and out of registers. The W's and X's are registers in ARM assembly, and in ARM assembly, you pretty much have to do everything in the registers. So if you want to change anything in memory, you take the memory contents, load it into a register, modify it, and then write it back out to the register. So it takes 3 or 4 commands to do everything that would often be one command in Intel, because ARM is a reduced instruction set computing, so that's why it's faster and uses less power. The individual commands do less, and there are fewer of them, and it takes more commands to get something done. But that turned out to be more efficient than the Intel large instruction set computer, complex instruction set. So you can search memory. Let's see if I can copy and paste this one in. All right. This is one that's going to search and create file. If you look here, I should be able to find the pattern 3191 somewhere here. I think it's right there. Anyway, I can search for a certain pattern this way with my, there. You can search, starting at this location, NT bang create file, limit 100, bytes to search, and then search for this pattern of bytes, 3191. And it found it here, 3191, at 8:15. And so if I look here, 8:15 is down here, and there it is, 030191. Remember, it's little endian again, so the order is reversed. So you can now find any byte pattern you want to by searching for things. This, unfortunately, that command I said I loved from OllyDbg, search for referenced text strings, it doesn't seem to exist here. At least I couldn't figure out an easy way to do it. But you can look for strings. You can do, you can search for ASCII strings with this one. Search -SA will search for ASCII strings starting there and going for 100 bytes. And so it shows me all the printable strings. And in this case, there are no actual sensible printable strings. There's just a series of bytes that happen to be printable that are all just garbage. And you can see the strings that are longer than a certain thing. And all right. And so if I want to get things that are longer than, say, 6, I can take that same command and I can, this is what you do, -bracket L6. This is why I say you really have to read the help file because the syntax of these commands is mighty screwy. This will look for strings of lines of length 6 or more. Now, I'm not going to find any because, as you can see up there, they're all shorter than that. But if I search for a longer range, like 1,000, then I will find one. Again, it's just random characters. It's not an actual meaningful string, but all right. And you can display memory. If you do DB, it will show you memory the way we're used to seeing it in both binary and ASCII. And this, you'll notice, is the beginning of NTOS kernel. And NTOS kernel is just a Windows executable, like all the others we've looked at. So it starts with the MS-DOS marker and the MS-DOS stub header, and down lower will come the NT header and all the stuff. It's a portable executable file, just like the others we've examined. The kernel is. Now you can look at data structures. So a file is a data structure in the kernel, an abstraction, of course, to refer to a file stored on the disk. So we can examine the structure of a file object. And this is what I meant when I said you can use this tool to thoroughly understand exactly how every bit of Windows works and figure out how an undocumented function works. So here you see the type size. Someplace down here will be the flags and the file name and so on. This is the data structure of a file object. And all right. And you can view your running processes with .tlist. Here's the running processes, the same stuff you'd see in Task Manager. And the first process is typically LSASS. Thought I would find it there. Oh, actually, I'm going to do it by name. Okay, LSASS is the Local Security Authority Service that's always running, having to do with logons, and you can examine details of it with this command, bang process 00 of lsass.exe, and here it will tell me the process environment block, the parent process identifier or CID, which might be something a little bit different. And now the process environment block is here, and I can click it for more information, and that will just type in the command to give me more information about it. And I'll see more information about LSASS and stuff about the profile, the module path, and so on. Gives me a user profile it's running under, and so on. Lots of information about it. Now you can view devices and drivers. This is how you examine the hard disk. And there it is. And you can see I'm using a VMware virtual hard disk because I'm running in a virtual machine here. So on, you can get more information about it. And that's it. There's a few flags to find in there to turn in stuff, but this is the very beginning of how to use this kernel. You can actually write programmed scripts. There's one thing I've seen that I didn't put in the project yet. You can program it to tell you every time a file is created and print out the name of the file by having a sort of, you write commands, there's like ifs, there's loops and stuff. You can write a complicated combination of commands here that will do something like that. It will put a breakpoint at someplace like ntcreate file. Every time it enters, it will read the value of the file name, print it on the screen, and then resume execution. So you get a custom list of information. So you can really do a lot of sophisticated stuff in WinDebug if you get good at it. And of course, there's decades of people writing up blog posts and stuff with tricks of how to use this product. So that's what I wanted to show you. And let me stop this one.